Module 1, Lecture C, Logic and Flow. By the end of this lecture, you will be able to write conditional statements that model engineering thresholds and operating limits. Use leaps to repeat calculations for ranges of engineering values, and apply simple input validation to reduce invalid or unsafe calculation results. Engineering conditionals. Threshold decisions. Threshold decisions let programs apply engineering judgment by checking whether values are within acceptable ranges. Conditional statements use these limits to decide if a condition is safe, cautionary, or dangerous, such as when temperature is too high or battery charge is too low. This helps software respond consistently by continuing, adjusting, warning, or stopping when needed. Threshold decisions turn technical criteria into clear actions by comparing a measured value with a set limit. Engineers use this pattern to judge whether a beam deflection is acceptable, a shaft speed is safe, or contaminant levels meet regulations. In each case, the boundary guides the next step and makes decisions consistent. Threshold decisions must be defined clearly, including what each boundary means and how edge cases are handled. A threshold may represent a safety limit, design target, warning level, or trigger for more analysis, and each choice leads to different actions. Good decisions depend on the engineering context and on understanding what it means to meet or cross the threshold. Python code, threshold decisions. Use Python conditionals to compare measured values with operating limits and classify the results. This helps quickly identify whether a model or system is within acceptable thresholds and print concise labels for review. The script starts with a small set of Celsius temperature readings: 62, 78.5, 85, and 91.2. These values will later be checked against thresholds to classify how severe each temperature is. The system uses two temperature limits to stay safe: a warning limit at 80 degrees Celsius and a shutdown limit at 90 degrees Celsius. The warning limit signals possible overheating, while the shutdown limit triggers power off to prevent damage. This check confirms that the warning limit is set below the shutdown limit. This helps ensure the system gives a warning before reaching the point where it must shut down. If the warning limit is not lower, the settings are invalid and should be corrected before continuing. The code verifies that the warning limit is lower than the shutdown limit before continuing. If the thresholds are set incorrectly, it raises an error and stops execution, helping prevent unsafe operation. The program prints a brief message announcing that it is about to evaluate motor temperature thresholds. This acts as an introduction, helping the reader understand that the following output will report temperature threshold decisions. Each temperature reading is compared against two thresholds to assign a status. Readings at or above the shutdown limit are marked as shutdown. Readings below that, but at or above the warning limit, are marked as warning, and all others are marked as normal. This provides a clear way to classify temperatures and guide decisions based on their level. The code prints a brief result for each temperature reading. It shows the temperature rounded to one decimal place and the assigned status, such as normal, warning, or shutdown. This makes each reading's classification clear at a glance. This script checks temperatures against warning and shutdown limits to report system status. It first confirms that the warning limit is lower than the shutdown limit and raises an error if the limits are invalid. Then it labels each temperature as normal, warning, or shutdown and prints the result, giving quick feedback for temperature-sensitive monitoring systems. Threshold logic. Threshold logic helps a system turn sensor readings into clear decisions by checking whether a value is below, within, or above a safe range. For example, battery temperature or pipeline pressure readings can be classified as normal, warning, or unsafe. Conditional statements make these checks possible, guiding the program to respond appropriately to changing measurements. In threshold logic, each boundary must be treated carefully because limits come from real constraints such as material strength or safety standards. The logic must handle values that exactly meet a limit, not only those that exceed it. This helps systems, such as motor controllers, correctly distinguish normal, marginal, and critical conditions. Effective threshold logic must clearly organize decisions when a system can produce several outcomes, such as normal, warning, or critical conditions. Each range should be distinct and non-overlapping, so every possible value leads to one appropriate action. This structure makes the logic easier to test, explain, and trust by connecting numerical limits to consistent system behavior. Python code. Threshold logic. Threshold logic converts limits into decisions by comparing values carefully against engineering boundaries. In this example, it is used to classify battery temperatures. The setup defines battery temperature readings in Celsius and two limits for evaluation. Temperatures up to 40 degrees Celsius are treated as normal, while 50 degrees Celsius marks a warning level. These limits are used to classify each reading by operating status. Before classifying battery temperatures, the code verifies that the normal limit is lower than the warning limit. If the limits are set incorrectly, it raises an error instead of continuing. This validation prevents faulty logic from affecting the classification results. Each temperature reading is compared with set thresholds to determine its status. Readings below the normal limit are treated as normal operation, while readings up to the warning limit are marked as being in the warning zone. This categorization helps guide the appropriate response to different temperature conditions. When the temperature goes above the warning limit, the system marks the status as stop charging to prevent possible damage. It then creates and prints a clear message showing the temperature and its classification. This message explains that when the battery pack reaches 40 degrees Celsius, it enters the warning zone. It reinforces the code's threshold rule. Temperatures at or above 40 degrees require caution and mark the shift from normal operation to a warning state. The script classifies battery temperatures using normal and warning thresholds. It first verifies that the normal limit is below the warning limit, then labels each reading as normal operation, warning zone, or stop charging. It prints each temperature with its status, making the safety decision clear. A temperature of exactly 40 degrees Celsius is treated as entering the warning zone. Limit checks. In engineering programs, limit checks make sure calculated values stay within safe and meaningful ranges. Conditional statements compare measurements such as temperature, pressure, or current against allowed limits, then decide whether to continue, warn the user, or flag a problem. This turns engineering judgment into clear rules, so invalid values are not treated as acceptable. Limit checks in engineering should reflect real-world meaning, not just compare numbers. A value outside a safe range can signal different problems and require different responses, such as a pump flow issue or excessive bridge deflection. Conditional statements help classify results as safe, marginal, or unsafe, teaching that programming must judge whether outputs make practical engineering sense. Limit checks help engineering programs catch values that do not make sense, such as unrealistic sensor readings, impossible efficiency results, or negative measurements for length or mass. Using conditionals to flag these cases improves reliability and helps reveal sensor problems, bad inputs, or formula errors. This supports safer outcomes by encouraging engineers to verify assumptions before trusting results. Python code. Limit checks. Limit checks help keep engineering calculations safe, and conditional statements express the rules for acceptable operation. In this example, those rules are used to classify pump flow readings. 3 flow limits are used to classify pump readings: 20 as the minimum safe flow, 80 as the top of the normal range, and 100 as the point where flow becomes too high. These thresholds define the safety status of each reading. The process begins with a set of measured flow rates that will be checked against predefined limits. A separate counter tracks how many readings are unsafe, normal, or warnings, starting each category at 0 before classification begins. Each flow rate is checked against the acceptable low and high limits. Any value below the low limit or above the high limit is marked as unsafe, helping identify flow conditions that may need attention. This section checks whether the flow rate stays within the normal operating range. If it is at or below the normal limit, the status is set to normal, meaning the flow is safe and expected. Otherwise, the status becomes a warning, indicating the flow is higher than normal and should be monitored. The code keeps a running count of how often each flow status appears, increasing the count for the current status each time it is processed. It then prints a clear message showing the flow rate and its assigned status, giving immediate feedback for each reading. The code prints a brief summary of how many flow readings were classified as unsafe, normal, or warning. These counts were collected while each flow rate was checked against the set limits, giving a quick overview of the classification results. This script checks pump flow readings against safety limits and labels each one as unsafe, normal, or warning. Readings below 20 or above 100 are unsafe. Readings up to 80 are normal, and readings above 80 but below 100 trigger a warning. It prints each result as it runs, and then reports the total number of readings in each category. Engineering loops. Force iteration. Force iteration means repeating the same force calculation for changing input values to observe how a system responds. By using a loop, engineers can consistently study effects such as increasing loads on beams or brackets, or changing spring force with displacement. This structured repetition reduces errors and helps reveal overall system behavior under different conditions. Force iteration in programming turns repeated engineering calculations into a systematic loop. The input values change, such as loads, compressions, or wind speeds, while the calculation method stays the same. By processing each case in sequence, engineers can compare results, spot patterns, and make better design judgments. Using loops for force calculations lets engineers test a range of conditions instead of one fixed case. This helps account for real-world variation, such as manufacturing differences or environmental changes, and shows when a system may approach its limits. Repeated analysis makes comparisons faster and more consistent, supporting safer and clearer design decisions. Python code. Force iteration. Use loops to test forces across controlled engineering values and reveal trends as loads change. Validate inputs first to prevent unsafe or unreliable calculations. We set the spring stiffness to 250, which controls how much force the spring produces for a given displacement. Using a positive value keeps the spring behavior physically realistic, as it compresses or extends under applied forces. We define a set of displacement values in meters to represent different spring positions. These values are used to calculate the spring force for each case with Hooke's law, showing how the force changes as the spring is stretched or compressed. The operating force limit is set to 8.0, defining the maximum force considered safe in calculations. Any calculated force above this value should be flagged to support safe and reliable engineering work. Before the loop runs, the code checks that the spring constant is positive. If it is 0 or negative, execution stops with an error so the user can fix the input. This validation prevents physically meaningless values from producing unreliable calculations. Before the loop runs, the program checks whether the displacement list is empty. If it is, it raises an error to stop execution, because the loop needs valid data to process and should not run on an empty list. The code prints a clear table heading for the results. It labels the output with displacement in meters, force in newtons, and status, making it easier to compare the calculated force with safe limits. We loop through the displacement values to calculate the corresponding force using Hooke's law. This lets us see how the force changes for different displacements and check whether it remains within safe operating limits. The code checks whether the displacement value is negative. If so, it marks the displacement as invalid, so only non-negative values are used in later calculations. This code uses Hooke's law to find the spring force by multiplying the spring constant by the current displacement. The result is the force in newtons for that displacement. The code compares the calculated force with the safe limit. If the force is within that limit, it marks the status as within limit, helping prevent overloading. This code checks whether a calculated force exceeds the safe limit. If it does, the status is updated to flag the force as above the limit, making potentially unsafe values easy to identify and review. This output line shows each displacement value with its calculated force and whether that force stays within the safe limit. It formats the numbers to 2 decimal places and aligns them for easy reading, making results simple to compare across different displacements. The code ends by printing a brief summary that explains the loop's purpose, showing how force changes as displacement varies. This reinforces the main lesson that iterating through different values helps reveal the relationship between force and displacement. The script uses Hooke's law to calculate spring force for a set of displacements, after checking that the spring constant is positive and the displacement data is valid. Each non-negative displacement is converted into a force, then compared with a safe limit. The output summarizes the displacement, force, and whether the result stays within the safe operating range. While loops. A while loop is useful when a calculation must continue until a changing condition is no longer true. Instead of running a fixed number of times, it stops when the result reaches a required limit, such as a safe contaminant level, temperature, or negligible change in an estimate. This makes while loops well-suited for engineering problems where the endpoint depends on the outcome. A while loop works well only when its condition depends on values that change during execution. If those values are not updated correctly, the loop can run forever and hide mistakes in assumptions, units, or limits. In engineering tasks such as pump selection, a reliable loop needs a clear starting point, a realistic stopping condition, and updates that move the process toward completion. While loops let a program keep running until data is valid or a condition is met. In engineering tools and simulations, they can wait for acceptable inputs or update a system until it reaches a target state. This makes them useful for modeling dynamic processes where behavior changes over time, rather than following a fixed number of steps. Python code, while loops. Use a while loop to model a draining tank and continue the simulation until the concentration falls to a safe limit. At each step, update and track the controlled calculations so the process remains clear and accurate. The tank starts with a substance concentration of 120 milligrams per liter, and the goal is to reduce it to the safe discharge limit of 25 milligrams per liter. Each treatment cycle removes 30% of the current concentration, modeling the gradual cleanup process. The setup begins by creating a counter to track loop iterations, setting a 20-step limit to prevent an endless loop, and preparing an empty history list to record concentration values over time. The loop runs while the concentration remains above the safe limit and the maximum number of steps has not been reached. Each pass records the current rounded concentration, lowers it by the removal fraction to simulate cleaning, and increases the step count. This process stops when the tank is safe or when the step limit prevents endless looping. The current concentration is rounded to 2 decimal places to create the final reported value. This value is added to the concentration history, and then it is compared with the safe limit. The result is a true or false safety status, showing whether the concentration has reached an acceptable level. The code introduces an example of using a while loop to clean up a tank. It reports the tank's initial concentration before treatment begins, then shows the safe discharge limit that the cleanup process is trying to reach. The output summarizes the treatment process by reporting how many removal steps were completed, the final concentration in the tank, and whether that concentration is at or below the safe limit. This script simulates treating a tank by repeatedly lowering a substance concentration from 120 milligrams per liter until it reaches the safe limit of 25 milligrams per liter or less. Each step reduces the concentration by 30%, stopping when the limit is met or after 20 steps. It records the concentration history and reports the starting value, safe limit, steps taken, final concentration, and whether treatment succeeded. Looping engineering values. Looping through engineering values means repeating calculations across a range of conditions to see how a system responds. Instead of focusing on one result, engineers can identify trends in behavior as temperature, load, speed, or pressure changes. This helps evaluate performance, reveal safety margins, and support better engineering decisions. When using loops in engineering calculations, the chosen range and step size shape the usefulness of the results. Wide ranges show overall trends and possible transition points, while smaller steps give more detail in critical regions such as near motor limits or insulation thickness decisions. By applying the same process repeatedly, loops help engineers compare options systematically and reduce manual errors. Loops help engineers explore a range of values efficiently, instead of entering each one by hand. By producing results that can be reviewed and visualized, loops support analysis of how a system behaves under different operating conditions. This makes them more than a coding shortcut. They are a systematic way to connect calculations to physical meaning, reveal thresholds, and understand sensitivities before finalizing a design. Python code, looping engineering values. Use a simple loop to test different loads by repeating the same beam stress calculation safely. For each load, compare the calculated stress with the allowable limit. A set of 6 load values from 5 to 30 kilonewtons is defined for analysis. These values can then be used to calculate and compare the stresses produced by different engineering loads. 2 key constants are defined for the beam analysis: a cross-sectional area of 250 square millimeters and an allowable stress of 80 megapascals. These values are used to calculate stresses under different loads and check that the beam stays within the material's safe limit. Before running the stress calculations, the code confirms that the area is positive. If the area is 0 or negative, it stops and reports an error because the calculation would be invalid. This check ensures the remaining calculations use meaningful input. The code prints a short heading to introduce the axial stress load sweep results. This makes the output easier to follow by signaling that the next values are stress calculations for different loads. The process checks each load in turn and skips any value that is negative. This keeps the later calculations focused only on valid, non-negative loads and helps preserve their accuracy. The load is converted from kilonewtons to newtons by multiplying by 1,000. This keeps the force units consistent with the area in square millimeters for the stress calculation. The code finds stress in megapascals by dividing the applied force in newtons by the cross-sectional area in square millimeters. This shows how much stress the beam experiences under the load and allows it to be checked against the allowable limit. The code compares the calculated stress with the allowable limit. If the stress is within the limit, the load condition is marked safe. If it exceeds the limit, it is flagged as unsafe. This line prints a clear summary for each load case, showing the load in kilonewtons, the calculated stress in megapascals, and whether the stress check passes. The output formats the load as a whole number and the stress to 1 decimal place for easy reading. The script checks whether each beam load is safe by calculating axial stress from the applied load and cross-sectional area. It first confirms the area is positive, then converts each load to newtons and computes stress in megapascals. Each result is compared with an allowable limit of 80 megapascals and labeled either acceptable or over the limit. Validation logic. Safe input checks. Safe input checks help ensure calculations are reliable. Before using a value, confirm that it is present, has the right type, and is physically possible. This prevents invalid inputs such as blank entries or impossible engineering values from producing misleading results. Safe input checks separate basic acceptability from deeper engineering judgment. They confirm that values are usable, such as making sure a temperature is numeric, a count is a whole number, or a sensor reading is not missing. Catching these issues early prevents common errors, makes program logic more reliable, and gives users clear guidance for producing meaningful results. Safe input checks help engineering software avoid misleading results by catching values that fall outside valid assumptions. They can prevent errors such as impossible efficiencies or temperatures before calculations are trusted. These checks do not replace professional judgment, but they support disciplined analysis by making the limits of a calculation clear. Python code, safe input checks. Safe checks make engineering calculations more reliable by stopping invalid values early. Clear error messages help users correct problems safely and efficiently. The process begins with a collection of sample inputs that includes both valid numbers and invalid non-numeric entries. 2 empty collections are then prepared, one to store values that pass validation and another to store messages for entries that fail. This setup keeps accepted data and validation errors organized during processing. The process checks each raw entry along with its position in the list. It first removes extra white space, then identifies any entry that becomes empty. When an empty entry is found, a rejection message is recorded for that position, and the process moves on without further handling it. After checking that the entry is not empty, the code tries to convert it into a decimal number so it can be used in calculations. If the entry is not a valid number, it records a rejection message and moves on to the next item, allowing only valid numeric values to continue. The code validates each diameter by checking that it is greater than 0. Non-positive values are rejected with an error message and skipped, while valid diameters are saved for later processing. Using the validated diameters, we calculate each circle's area by multiplying pi by the square of half the diameter. The result is reported in square meters, with each diameter shown to 3 decimal places and each area to 5 decimal places for clear, consistent output. The code reports how many values were accepted and how many were rejected by counting the relevant lists. It then prints all rejection reasons as one semicolon-separated message, giving clear feedback on failed entries without stopping the program. The script cleans and validates raw diameter entries before using them in circle area calculations. It rejects entries that are empty, not numeric, or not positive, and records the reason for each rejection. For valid diameters, it calculates and prints the circle area, then reports how many entries were accepted or rejected. This helps prevent calculation errors and makes it clear which inputs need correction. Input range checks. Input range checks make programs safer by ensuring values are reasonable, not just the correct type. For example, temperatures and pressures should stay within physically valid and equipment-safe limits. These checks help prevent misleading results from calculations based on invalid assumptions. Effective range checks come from the real limits behind a problem, such as physical laws, equipment specifications, or safety standards. These boundaries show where calculations and assumptions are valid, such as allowable speeds or flow rates. By making limits explicit, programs help users judge when results are reliable. Input range checks help programs catch values that are too low, too high, or otherwise invalid before they cause problems. By giving clear feedback, they support timely corrections and safer engineering decisions. Although they cannot make a program perfect, they reduce costly mistakes and promote more disciplined, transparent practice. Python code, input range checks. Range checks help keep engineering calculations safe and meaningful. Their limits should reflect the physical assumptions behind the calculation, and clear error messages should guide users toward correcting invalid values. A list of sample sensor readings is stored as percentages to represent different states of charge. Some readings may be outside the valid range, so keeping them in one list makes it easy to check and calculate them later. Set the valid engineering range for sensor readings from 0 to 100. These limits define the expected physical bounds, so each reading can be checked as valid if it falls within that range. Begin by setting 2 counters to 0, one for acceptable sensor readings and one for unacceptable readings. As readings are checked, these counters track how many pass or fail validation, giving a simple summary of the results. Each state of charge reading is checked against the allowed range. A reading is considered valid only if it is at least the lower limit and no more than the upper limit. So only acceptable values are used further. The code verifies that the current state of charge is within the allowed range. When a reading is valid, it increases the count of acceptable readings used for later calculations. After confirming the sensor reading is valid, calculate the energy factor by comparing the state of charge to its maximum value of 100. Then, report that the state of charge is valid and show the energy factor rounded to 2 decimal places. When a state of charge reading is outside the safe range, the invalid count increases by 1. This tracks how many readings fail validation, making it easier to summarize the results later. The code explains that a sensor reading is rejected because the state of charge is outside the allowed range of 0 to 100%. This message helps users identify the safety limit issue and correct the input. The code summarizes validation by reporting how many sensor readings were accepted and how many were rejected. This gives a quick view of overall data quality and shows how many values fell within the allowed range. The script checks sensor readings given as percentages to see whether they fall between 0 and 100. Valid readings are converted into an energy factor by dividing by 100, while out-of-range readings are rejected with a warning. After all readings are processed, the script reports how many were accepted and how many were rejected, helping ensure only safe data is used in later calculations. Handling unsafe inputs. Handling unsafe inputs means stopping or flagging values that are invalid or risky before they produce misleading results. In engineering, this is especially important because unusable data, such as an impossible physical value, can lead to unsafe conclusions. A good response clearly identifies the problem, avoids treating bad data as valid, and guides the user to provide accurate information about the real system. Unsafe inputs should be caught before calculations continue, because they can create misleading or physically impossible results. Validation should stop values that break assumptions or exceed practical limits, such as impossible temperatures or unrealistic rainfall intensities. Clear feedback helps users fix the input and supports sound engineering judgment. Unsafe inputs should be handled carefully by asking for the value again, using a justified safe default, or logging the issue for review. Rechecking is important when accuracy matters, while defaults should only be used when they will not hide serious problems. Logging helps reveal repeated issues across many data points, supporting reliability and safety. Python code handling unsafe inputs. Always validate inputs before performing engineering calculations. If values are unsafe, the process should stop rather than produce results. Clear messages should help users correct the problem safely. We define a sample set of pike diameters in meters that includes both valid values and flawed entries, such as 0 and negative numbers. This prepares the data for later safety checks against allowed limits before using it in engineering calculations. A list of flow rates in cubic meters per second is stored for later use. It includes both valid positive values and an intentionally invalid negative value to test how unsafe inputs are handled. This makes it possible to check the data against safe limits before using it in calculations. Set safe limits before running the calculations. Pipe diameters below 0.05 meters are rejected as unsafe, and flow rates must be non-negative and no greater than 0.05 cubic meters per second. These limits keep the inputs realistic and safe for later calculations. We organize the results into 2 groups, one for speeds that pass the safety checks and one for cases that fail validation. This keeps reliable data ready for later analysis, while recording which inputs were rejected and why. The loop goes through each diameter and flow rate pair one at a time, using enumeration to keep a human-friendly case number. In each pass, it separates the pair into the current diameter and flow rate, preparing them for validation. The code rejects any case where the diameter is below the minimum safe value. It records the case as unsafe, skips the remaining calculations for that input, and moves to the next one. This keeps later results based only on valid data. The code rejects any flow rate that is negative or above the maximum safe limit. When this happens, it records the case with an out-of-range message and skips to the next input. This ensures that only valid, safe flow rates continue to later calculations. After validating the inputs, the code finds the pipe's cross-sectional area using the circle area formula, with the radius taken as half the diameter. It then divides the flow rate by this area to get the flow speed in meters per second. Finally, the speed is rounded to 2 decimal places and stored with the case number as an accepted result. The output first labels the results as validated pipe flow speeds, making clear that safety checks were applied. It then shows the accepted cases with their case numbers and calculated speeds, followed by the rejected cases with the reasons they failed, such as unsafe diameter or flow rate values. This separates safe inputs from unsafe ones and explains why some cases were excluded. The code highlights why validation matters in engineering calculations. By filtering unsafe inputs before analysis, it helps prevent incorrect or misleading results and keeps the calculations based on reliable data. This script checks pipe diameters and flow rates against basic safety limits before doing calculations. It rejects pipes under 5 centimeters wide and flow rates that are 0, negative, or above 0.05 of a cubic meter per second. For valid cases, it calculates flow speed from the flow rate and pipe area, then separates accepted results from rejected ones with clear reasons. The main point is that input validation helps prevent misleading engineering calculations. In this lecture, you learn to write conditional statements that model engineering thresholds and operating limits. Use loops to repeat calculations for ranges of engineering values. And apply simple input validation to reduce invalid or unsafe calculation results. In the next module, Module 2, we will go over data structures. Thank you for your attention. See you all in the next lecture.